All right, physics reaction video number 24. Today, I think, based on this, I think it's a study session. Maybe just a few problems got to be worked, so let's see how it goes.
Grading, just try to make the day before a test. I wanted to reach out to some people on Zoom and weren't able to get in, so this is I just want to talk about a few quick problems here. Basically 27 and 45. Because it's a kind of problem where a lot of what you're learning in 27, even though 27 is kind of brutal the first time you go through. We're going to look at 45 here.
So I'm not sure if the students have already seen this. I wonder if this is like some solution that he's already provided to them, because it doesn't sound like he's going to talk about every one of them. But even if it's not, even if this is the first time they see it, I don't have a problem with showing the whole thing, which might be intimidating to them, and then slowly walking it through. And of course, a student can say, the only part I was confused about was here. And they can just fast forward. You could see his finger every once in a while, just like, or, if I'm doing this on my screen, you'll see my cursor. The students could fast forward until the finger or the cursor was down where they're confused. I think that could work just fine. I'm not 100% sure what's going on here. It looks like this problem is some sort of, hey, how fast is it going at the bottom, or maybe how far does it go, something like that.
First, because 27 is basically just a little bit more complicated version of 45. And so 45 is they have a slide where somebody is starting at a specific height, capital letter H. They're sliding down and they exit horizontally at a height of lowercase h. The difference between this and number 27 is that the girl that's going down the slide actually goes up at an angle, and you have to find the max height she is. So that's that complicated.
So it sounds like there's a couple of problems that have similar questions being asked. The thing that I like about this is I actually don't think the shape of the slide matters. All we know is how high it starts and compared to how high it is at the bottom, and we know it's horizontal here. Well, there is a gajillion slides we could do like that. You go way down here, come back up again, and then go horizontal. I guess the only thing we can't do is go up at first. Right, we basically can't have the slide go above this line right here, because then whoever's on the slide would not go over there. So basically, you can draw anything you want. Are you allowed to go over here? Are you allowed to go zigzag? Are you allowed to cross? Are you allowed to go loop-de-loop? As long as you come out horizontal here, you'll get the right answer. Now, how did he draw it? He drew it sort of smoothly, whatever this graph is. Maybe it's a parabola. It's probably just a scribble, right? Because this is the experience that our students have. But it's interesting to think about how it doesn't actually matter based on if you look at how the calculations are going to go here. All that matters is capital H, lowercase h, and probably implicitly somewhere in here it's going to say that it's heading out horizontally.
Things, but the basic of how you would set this up is similar for both of them here. So the first thing we need to do, and this is the very helpful, is to think about if we can write an equation for the energy anywhere on the slide. That is the equation basically the energy everywhere. So for example,
cool.
So hey, how do I create an equation for the bottom or the middle? Look at the top, because if you look at the very, very, very top, the person down the slide is not moving. And if they're not moving, there is no kinetic energy.
Love
so
it.
Your equation is only gravitational potential energy, which is mg times big H, because you're up the top there. So here's the realization that you can use this energy as your total.
So I'll be honest, the very first thing that I did was I was like, huh, what? Because I was assuming there was going to be a capital H minus H somewhere. And I can see it now, right? He's defining the zero of his potential energy to be the floor. And, we're always talking about scaffolding for students and trying to think what are ways to sort of say, look, if you're ever stuck, just try doing this. And certainly the notion of setting the zero of the potential energy to be right here is going to work for you, right? I think if I had done this problem, I probably would have done mg capital H minus H, maybe, or, now that I say that, I'm not sure which way I would do it. I might do it this way. What's so fascinating, I think, struggling for students is that when they get into gravitation, all of a sudden, for some reason, we set the zero potential energy out at infinity, like as far away as you can possibly be. And the students are like, well, I want to set it at zero. And we're like, your calculator's going to barf on you if you set the zero potential energy at r equals 0. What do you mean? Try it. right? And they're like, oh, my calculator barfed on me. So this notion of where we put the zero of the potential energy is so fascinating. It's always, better be careful. What the hell? It's always where it makes your life easy. That's it. It's where it makes your life easy because it doesn't actually matter. All that matters are differences. Okay, cool.
Total energy, because at the top you only have mgh, and that is equal to your total energy. So that means, since total energy doesn't change in a isolated system here, that anywhere along here, including the bottom, is equal to mgh. Now there's equations here, but you can set the two equal to each other.
Cool.
At the bottom, we have kinetic energy because it is now moving, so 1/2 times mvi. They use vi in the book because you have to calculate a projectile here, so it's your initial velocity when you exit the ramp. That's why it's vi. So you have your kinetic energy, which is the 1/2 mass v squared, plus whatever your potential energy is left, because you're not all the way down at the bottom. If you're all the way down at the bottom, there is no energy, but in here we have mg lowercase h. This is our equation right here, and we have to realize if we want, what we're trying to do here is we're trying to set up what is h, basically what is big H, how high you have to be up there in terms of D and H only. And you're thinking, what equation do I have? Or sorry, what is what D is? D is this distance right there. Or as a projectile, it.
Aha! That's why he set the zero potential energy to be at the ground. I was like, what? Huh? Aha! Now I get it. So he says that over here there's this separate problem that basically looks like this. And there you're going to have lowercase h. Again, you could have set the zero potential energy to the bottom of the slide, but then this would have been like a negative height or something. Okay, very, very cool.
It is your horizontal distance, it's your range. So in terms of how far horizontally it goes and the height at where it launches, how high does this have to be right here? And so this isn't in order at this point, but realizing that what we can do is we can set the two equal to each other here. So let me get a blank paper here. That the energy, total energy of this.
Look at that, recycling. You can tell there's something on the back of there. Challenge to my viewers. What the heck is written on the back of this? I bet you can tease it out. What else was I going to say? Oh yeah. So this problem is literally what I did in high school. We had an indoor balcony in my high school, Hopkins High School. We had an indoor balcony. We built a slide just like what they have here, and the teacher put a coffee can way down at the bottom on the first floor, and it was like a class quiz. They're like, everyone on the first day, you picked a spot, you marked a spot here where you were going to put your marble, and then you were going to come back the next day and absolutely put your marble there. And then he had someone in the class measure the height of the balcony. And the next day, all you had to tell him was where to put your bucket, the coffee can, down below. And then you'd go put your thing on here and clunk. And if you got it in, you passed. If not, I actually don't know what happened. There were two different versions of it that year. And so you could choose to do the air resistance version, which just meant a smaller coffee can. And so he gave us some air resistance equations. I don't remember exactly how they worked. I remember being like, oh, okay, I'll plug and chug. But here's the fascinating thing. Everybody missed. Every single student missed. And he was smirking off in the corner, I'm pretty sure. Because I'm sure he's done this year after year after year after year. What had happened was the students who we had trusted to measure the balcony height had gotten it wrong. And I'm sure that Mr. Erpelding knew what the height of the balcony was, but he let us run with a bad number. And we all missed. It was actually really, really interesting to see how crabby people can get. But as I recall, he did some sort of, actually it's okay in the end, which probably was smart. My blood pressure was up for sure.
There, mgh is equal to the total energy at the bottom, which is 1/2 m initial velocity when it's launched from the slide plus the gravitational potential energy at lowercase h. Now we can only have an equation with d, big H, and little h. So here, mass cancels out.
Oh, I love it. And of course, what I always tell my students, if something cancels, you got to be able to say something, right? So we're super happy when things cancel, super happy. But to me, mass, mass, mass cancels. Apparently, you get the same answer no matter what mass you start with. In a similar way, occasionally G cancels, and when G cancels, all of a sudden, you can do this on a different planet. Looking at his answer, it looks like G disappears. So that's this example. You get the same answer independent of what planet you do this on. That's pretty cool.
I'm going to go ahead and rearrange the equation real quick. So to solve for H, it's not this symbol. There's a lot more work we have to do. But it's 1/2
That was awesome.
VI squared over G, because you G for there, plus you divide both sides by G. Oh, let me do it this way. Sorry. 1/2.
Oh, yeah.
And
Nice.
then you divide G over here, and it cancels that out, so plus H. And interesting enough, that H is going to stay there. So there's where our H is. We need to figure out what is this velocity here.
So it's actually interesting here because he's already done this. Maybe he just didn't like the way that he had done it on the other sheet of paper. So let's see, we're at 440 right now. I'm going to go back to before he had the extra sheet. There we go, somewhere around here. All the work to get what VI is down here, and then he used this big arrow to stick it up in there. And then he got rid of M, and then he got rid of G, and then he got his answer. So it's interesting that he's choosing to do it another way. And I'm guessing it's one of two reasons. Either, one of three reasons. Either there's actually something wrong here, and he realized, oh, shoot, I need to start with a clean sheet of paper. That's option one. Option two, he did this a while ago and didn't quite remember what was going on. He thought, you know what, gosh, we better solve for, get some capital H's in here right away. And number three, purposely knowing that students should see a couple of different ways of doing things. I mean, it's not that different, but like, I've already shown you this way, let me show you a new way. So that's really intriguing.
It's your range. So in terms of how far horizontally it goes and the height at where it...
Sorry. Let's get it back to 440. Close enough.
Required. And this is where we use some projectile motion problems. Now, it's simpler than number 27 because it's just a horizontal launch, and that's nice because there's no components of velocity in the, I guess there's no components in the velocity initial direction.
So it looks like he's coming back to this page now, and he's like, you know what, now this stuff will make sense. It's interesting that he's, down over here when he follows this arrow back up, he'll have to cancel M again. I'm curious to hear what he says. Let's listen carefully. When he gets back up to here, he might say something like, "Oh, well, we already did this," or "Oh, yeah, we talked about G already," or something like that. But I think what he felt was this was coming out of nowhere, so he needed to do a little bit more work there. This is really interesting.
And so in the X direction, I was kind of doing this here. Let me refocus it here. In the X direction, we have our velocity. The velocity in the X direction is how far it moves, distance over time, or delta X over T, how we might have used it here. So when I solve for time, I get the distance over the initial velocity in the X direction. So that's important right there. We're going to keep that. In the Y direction, there is no initial velocity in the Y direction because it's a horizontal launch. The angle, sine at 0, 0. So VIYT, in my class, this was the third equation. Delta Y is just this height here.
Did you hear that? He said, in my class, it was the third equation. I might be reading too much into this, but I wonder if some of these students don't have him. Like if this is some sort of like extra piece for students who have a couple of different teachers. Let's listen to that again. Go back. Listen to how he says my class.
There is no initial velocity in the Y direction because it's a horizontal launch. The angle, sine at 0, 0. So VIYT, in my class, this was the third equation. Delta Y is just this height here. And we'll go ahead.
Yeah, I mean, maybe I'm reading too much into it, but I feel like if all of these students were his students, he would have said in class. Why say in my class? That's really interesting.
And use positive, so that's positive, that's positive. But that goes to 0. You have delta Y equals 1/2 GT squared. You rearrange that to solve for t, and there's your equation right there. And so we need to now, here's the thing, we talked about this in my pre-physics classes. The one variable that doesn't have a direction is time. And so those two can be set equal to each other.
Cool.
You do a little bit of algebra. I'm not necessarily going to go through it here. I need to get VIX, so I'm basically going to invert both of these. Let me go back a little bit here. Okay. I'm going to invert both of these. My camera's running slow. Flip that upside down, to get to here. And then I solve for VIX, and this is my equation for VIX.
Cool.
So what you're doing is you're plugging that.
Let me take a look at that. So this is the equation for how fast you have to be going horizontally at the bottom of the slide in order to travel a horizontal distance d before it falls an additional capital H. So obviously if d gets bigger, v has to be faster. If you're on a planet with more gravity, you have to go faster. Oh yeah, because that'll suck it down faster. And if you aren't going to fall as far, so let's see, if h was shorter, you'd have to go faster. Yeah, okay, cool.
That into that right there. And I have it over here. I kept messing up a couple times. That's okay. I was just like, I can't do math. So here's me doing that. Here I canceled out the m's.
Uh-huh.
I plugged the value of VIX in there. It is squared because it is kinetic energy. When you do that, D becomes squared. Let's see here. Yeah. D becomes squared. G stays on top. 2H goes to the bottom. This 1/2 eventually becomes 1/4. And then G's are in all of them. G, G, and G. And so those cancel out.
So that was really interesting. I was waiting for him to say something about that. So he said G's are in all of them, G, G, and G, so you can cancel them all out. I actually think it makes more sense to students to cancel it here than to do what he did on the other page, which was to have this G in the denominator for a little while, right? Here it's like, sure, the G's all cancel. And that's where, by the way, we can tell that if you took this whole contraption and put it up on the moon, the same thing would happen. And so what's tricky about this is, how can that be? We know that the dynamics on the moon are different. We know it, right? Everything seems weird. All these videos of the astronauts on the moon look funny. And it's because G, the G on the moon is quite small compared to what we're used to. And so you might look on this page and say, what the heck just happened? And really, the only place where it's going to play a role is over here, these two circled things, right? So the time that it takes to do this entire experiment is going to be different on the moon. And let's see, yeah, the G is going to be smaller, so T is going to be much longer. So this whole thing's going to go in slow motion, but where it starts and where it ends will be at the same locations.
And you're left with 1/4 D squared over H, small h, plus H, or written down as that. So that's a lot. Let's break it down again. How do we even get this equation right there? And it goes back, and this is really important here, that the total energy at one place has to be equal to the total energy of other place for the isolated system. There's no friction, and by the way, there's no friction in this problem here.
By the way,
this is the bottom. This is the total energy at the bottom. I don't know how you use, and that's the total energy at the top, and those things have to be equal to each other.
So it's curious. I'm wondering what would happen if he had a student of, well, why can't we just do total energy at the top equals total energy at the very, very, very bottom, right? Because the potential energy there is going to be 0. So we'd be able to tell how fast it was going down at the bottom, but the problem is we wouldn't know the angle. And so this way, there was this really important point at the bottom of the slide where it was going nice and horizontal, so that made our lives easier. And you didn't have to worry about the angle that the thing's going now. But now you could figure that out after doing all this work.
And so we have an equation for the total energy in terms of the height of the slide at the very beginning, and we have the total energy in terms of the speed and the height of it at the very end, and that is really good because that gives us enough information. The last thing we did is like, we need to figure out what the velocity is, and we use some kinematic equations here to solve for what the velocity would be.
Cool.
And then plug it. It's just about simplifying.
That's a really interesting point. This is an energy problem, but then still needs some kinematics, as he's saying, right? So there's still, this nasty equation, which sometimes when you shift over to energy, this sucker goes away, and you have really easy, your life is easy because all you have is this straightforward one, time disappears. So usually when we shift over to energy, often time disappears. But he's saying, we had to go back to some old work of ours, right? So this stuff still works and proved to be quite useful here, and I really, really like that. I think I'm going to pause here. What I really liked about this problem is sort of revisiting something that likely the students had already seen. I loved the idea that he sort of had to plug his brain back in again, grab that other sheet of paper, because I think he felt like the way this was laid out just wasn't as smooth as he wanted it to be, and so he grabbed that other sheet of paper. I thought that was really cool. I loved the big idea, right, that the energy at the top is equal to the energy at the bottom. And then I find it fascinating, some of the extensions you can do. Really quickly before we end, if you ask the question, hey students, if you have to go out further, would you expect the hill to be higher? Yes, I would. But when you ask the question, yeah, but if I take the entire slide and raise it up, so I'm thinking of lowercase h here, what should we do if we raise it up? Can the slide be less tall? And the problem is, right, it's tough because it's both sitting here and it's sitting down here. And so that's a struggle when we're asking students to really think about, what affects things. In so many other places, you get just simple fractions like this one, right? Simple fractions we can say, you can even ignore the square root. You can just say, hey, does it make sense to you that if h goes up, t goes up? And does it make sense to you that if g goes up, t goes down? But when h shows up in a couple of different places here, actually what I'm dying to do is to take a derivative, right? So we could ask, where's the maximum point? So if you do dh, the derivative of capital H with respect to lowercase h, and set it equal to 0, what are we saying? Yeah, so there's the height of the slide is a really interesting function of h, and so there's must be a really interesting point that maximizes things. So cool stuff. All right, everybody, thanks so much. Have a great day, and remember, physics teachers are awesome.